Yeah, so I had a different idea first, but then Jacob made this for me, so I thought it was amazing. So we'll see where we get. Uh, Originally, I wanted to talk about ring buffers in my FLAC decoder thingy that I built in Rust, but now we're working with Servo instead, which is much cooler. So this is we're going to dissect the work queue for the layouting part of Servo, and this is where you would like to use the unsafe parts of Rust to build safe abstractions and do things that are not really safe, but you can kind of prove that they are safe, and from that build a safe API that others can consume and make nice programs that we like. So there's a lot of like strategies for concurrency, and a lot of them are going to be used in Servo. It uses everything from for like the DOM APIs to using a copy and write structure that allows the JavaScript and the layout to work on the DOM at the same time. There's concurrent rendering. I'm not really sure how it's done. Tiled rendering, layered rendering. They use all of these magic techniques that browser engines would like to use. But one of the things that have been really hard for traditional browser engines have been to do like parallel layout. Like different parts of a web page can be laid out in parallel in theory, but in practice no one has done it, except in Servo. So we're going to see how they do it. They're using it with this fancy work queue, which uses work stealing, fork join, lots of buzzwords. And well, that's it essentially. So we're going to see what parts and what kind of things you have to do to make these weird abstractions, and you can see that we're going to build it up from two primitives. The atomic uint, which is of course an unsigned integer that we can do atomic operations on, and the deck, which is a double-ended queue for, well, it's called that because some computer scientist thought it was funny. It's not funny. No one's going to figure out how it's pronounced or what it actually means. So the first part we'll look at is like how is a unit of work defined here, or a work unit, whatever. Everything that's put in a queue is a Rust function, which doesn't have any context, and a context. There's also actually the queue itself has some fancy context, which could be anything, but in Servo I think there's some hints that it's integers, but it could be anything. The typing means that it could be anything. We're going to jump down a bit. Oh yes, my numbers match up. Great. And we'll see the corresponding thing is like each worker thread has some data. We know the index of the worker, so well, it's useful later. One of these ports for a channel that we discussed earlier, and a sender. So this is the communication port that we receive things from the supervisor, which controls the work queue, and here is where we send things back to the supervisor. And we have the rear end of all the other decks. So a deck is a double-ended queue. Do we have? I have a pin. It essentially works like a linked list, a doubly linked list. I'm not sure if that's how it's implemented, but so the worker pops from the front, and then it steals from the back end. So it tries to empty its own queue first, but if it can't find any work to do in its own queue, it steals from the other ones, because they're nasty thieves. Those worker threads can't stay out of other people's business. So we're going to see how it looks when we first. It's going to be important that this thing is. I was pretty sure I have line 268 mentioned in mine. Oh yes, I have line 268 here as well. So when we push something onto the work queue, we actually only push the first deck, and that's important because we pushed a lot of things in the beginning to the first deck, but due to the work stealing, the other workers can take from the back of it. So it works out fine even if we have this very simple implementation. This is based around that each worker, when a worker does a piece of work, it not only finishes a specific piece of work, but it might also generate more work. So for example, if you're trying to lay out a div, it might find more divs inside of it that it can do in parallel. So the idea is that everything's done like on the first worker, but then all the extra work is being more and more spread out. So this is like really simple. If we want to push something onto the work queue, it just pushes onto the first worker's queue. And well, we increment the work count. It's like super simple. It's essentially like you would probably do it in C++ or something. There's nothing very special about it. We're not even touching unsafe code yet, so we're and my mouse isn't placed there. So when we start running this work queue only supports synchronous API, so it starts running when we execute run, and it runs until it's finished or someone else tells it to stop. We just create one of these atomic UINTs with the work count. We send a start message to all the workers, and we include the work count. And then we just wait for everything to finish. That's all there is to it, essentially, except that there's a lot of things to it. Because, as you might see, we're on line 200 something, and there's actually the most important thing here is how do we actually implement our work queue. This goes a bit out of. No. Oh. So all the workers are in a loop. Well, start a loop, and they start waiting for a start message. So the thread pool is created and everything, and it gets a start message containing its deck. I'm not sure what the reference count is. It's actually the amount of work there is. and the queue data, which is this, you might call it user info or something in C instead of queue data. It's just a piece of data that is specific for this queue, and your work is going to need it probably. I still need to learn where my mouse is. And here is where we get into the unsafe parts. You'll notice that in most Rust code you never use unsafe, hopefully. But when you're building these abstractions for your program, and you want to keep your unsafe in this abstraction. For example, here we create a piece of uninitialized memory. It's essentially a piece of uninitialized memory, kind of like when you allocate a struct or something in C on the stack. It's uninitialized and doesn't, well, contain anything. It's not something you would generally do. So I think this might be some sort of optimization, or it says nasty workaround, which is always a bad idea. You should try to avoid those, especially in code that's marked unsafe. So we look at our deck and we pop the first unit of work, either there is some work, and then we assign our work unit that work, which means that the uninitialized memory isn't uninitialized anymore, so we have to make sure. But if there isn't any work in our queue, we'll just steal some work from someone else. I mean, they shouldn't get the credit if they can't keep up. I mean, we're very fast and we can very. So we'll do a loop because we don't really know if someone else has any work worth stealing. So we'll randomly select. It's called a victim here. I'm not sure if I would feel like a victim if someone made my work for me, but I would see it more as a nice person. So we take the other decks and we try to steal from the victim. If it's empty, or abort is something that the deck returns if there's a race condition. If instead of blocking and taking a lock, it actually just aborts and lets you try again. It's an implementation detail of this specific data structure in Rust, in this specific implementation of it. I guess you could do it in some other way, but with locks or something, but we don't really like locks. Or we get a piece of data and then we assign it to work. And then there's some sort of back off that we don't really like. Notice that there's more unsafe here. This doesn't really seem unsafe, but the reason why it's unsafe is because uSleep is actually a C function that we don't really know anything about. So it's part of the C standard library, and it doesn't have a wrapper in Rust that says it's safe. It doesn't have this attribute, so we have to mark it as unsafe. I think there is similar functions in Rust that you could actually use instead, but for some reason they decided to use this unsafe version. My mouse. And if we go through this loop too many times, we'll just we'll check if we should continue. Like maybe all the work is done, or we're told to exit, or well, this is one thing that's going to be weird about Rust, is that in some cases there's no like sane thing to do, and then we call it panic. It's called fail before, and this just kills your entire thread. It runs all the destructors and everything, but it kills your thread. Nothing you can do to catch it. Yes.
Only the thread and not just the whole process.
No, just this thread. it doesn't kill the entire process. It just kills your current task or thread. It's only recoverable at task boundaries. But generally, you shouldn't do weird stuff and panic in the middle of it. Like you shouldn't like if you're implementing a lock yourself, you shouldn't panic while the lock is held, because then it can't really unlock itself. Or I mean, there's a lot of things that you shouldn't do while panicking. It can be bad if you're doing multi-threaded stuff and well, panicking at the same time. You should try and avoid it, but in a lot of cases, it's just the most useful thing to do as well. Like if you're for example, having a specific task for doing an image decoding, and the image file is corrupted, there's maybe not much you can actually do. I mean, it's not recoverable, and the only thing your program is supposed to do is decode this image. It can panic as well, just as well as actually trying to handle it. And then we just invoke this the work units function with the data and the proxy. That's everything, except that we. It's the slightly important part is that we take the amount of work we have in the queue, which, as you remember, is an atomic. So we fetch and subtract 1. This is the ordering requirement. On x86 it probably does nothing. And if the old value was 1, then all the work in the entire queue is done. Then we send a finish message. And when we're finished, we send we give the dex back to the supervisor. So it can the work queue can be reused for, like, if we go to another web page. This part. It's because all atomic accesses are unsafe, because they essentially refer to a piece in memory, and you're dereferencing a pointer, which is in theory unsafe. There has been a lot of talks about if atomic accesses are probably safe. Like atomic, as long as you're doing arithmetic and stuff, it's in practice safe. And there has been a lot of discussion if this should be considered safe or not, but for now it's unsafe. It's just a weird. It's just what do you call it? Like you have a rule and you decide that pointer dereferences are unsafe, and then the rule suddenly applies to things that are actually safe, and it could be fixed easily. But it's more of a, should we make the rules have exceptions, or should we just force people who are using, I mean, once you type in stuff like sequential consistency, you probably it could be error prone anyhow, so unsafe isn't really that bad idea. I mean, that's essentially the entire data structure. There's a few like helper thingies, and there's some setup in the beginning, but this is essentially how you could build an abstraction for any kind of communication between threads that you would do in like C and C++. And it's not inherently more safe, but you can build these abstractions that are more safe, and that you can use the type system to enforce certain things. Like these tasks, for example, are enforced by, these decks have the enforcement in the type system that you can only pop from the front of the queue from one place, but you can steal from all of them. And a lot of these things you can enforce in the type system, which you can't in C. And a lot of other things that you can do in, well, you have to document in C can be enforced by the type system in Rust. For example, send here means that it can be moved from one task, well, from one thread to another safely. And this is enforced in the type system, while in C you would have to document it and make sure that everyone reads the documentation and keeps it updated all the time, which I'm sure more people than I are too lazy to do, because multi-threading is really hard, and just having hard work is enough, and avoiding to update the documentation feels nice. If the compiler really throws up in your face instead, it's much nicer, because then no one else has to know that I fail. This setup is essentially nothing interesting, but it's just that we spawn all the threads and all that kind of silly stuff. Does anyone have any questions on like anything? Like,
There's a place where it's the ampersand prime static string.
oh yes, it's I can explain that. It's here, right? Okay, string is well, str is a string type. This means that we have a borrowed string, but the prime static means defines a specific lifetime, and static is a specific lifetime that says that it's statically allocated. It's read only and allocated in the, well, I'm not really sure where the linker would put it, but it's statically initialized and in read-only memory at the start of your program. So the linker fills these in. Generally, this means that we have some extra things we can do with them, but we can't, for example, change them, and they're deeply immutable, for example. Otherwise, you'll usually see lifetimes such as prime A or something. I can't type, sorry. And these are user-specified lifetimes, which says that if we said that work queue had lifetime prime A, this is going to have to at least live at least as long as the work queue we're creating. But static outlives the entire program, so if we have that lifetime, it's fine for everything and makes some things a lot easier. Sorry? Oh.
Signature.
Here?
Yeah, you said that defines that you can send it on a channel.
Yes.
Is that a keyword or is it specified in the lib somehow?
It's actually not a keyword, but it's not really specified in a lib. It's there's some things that are kind of in the middle. They are defined by the compiler, but you can. So this is special in the sense that if it's implemented or not, it's defined by the compiler, but you can. It's partially implemented in the standard library. So if you provide your own standard library, which some people do, you can implement things on top of this that are. So it's kind of special, but it's not keyword.
How does the type system know that it's safe to have all the threads have references to the same deck, or the type system know that that's safe?
It's actually the type system doesn't really know it, but it's if there as a specific deck can only exist one copy of the end you pop off. There can only exist one. You can't clone it. You can't give a reference to anything. So the type system, when you create that abstraction, you make sure that no one can get, that there can't be two two poppers at once. While the stealing end, you can clone. We'll see it down here. Is that I'm pretty sure it's called the thief? No. Yeah, here. Here. So this one we can clone, which means that we have multiple copies of this one, but we can't clone the other end. So that's how we enforce that there's only one popper, but multiple thieves. Yeah. So and this clone method is probably unsafe, which is why you're allowed to do specific weird things.
Yeah, I think it's safe. It's just that it's just senders inherently.
No, but I think the implementation inside of here is unsafe.
Oh yeah, okay, sure.
I mean, this part is safe, but the abstraction inside of this method probably isn't safe. So you have to make sure, when you break the rules, you have to decide what rules you provide to others. There's a few other of these like special traits like send, like for example copy, which some types implement, which means that it can be copied in memory, like a memcopy, and you can get a new, well, like for example ints are copyable and you get an identical copy. And such things. I don't remember all of them. There's quite a few.
So does this mean that send is a trait?
Yes, it is a trait.
I thought it was some kind of lifetime specifier.
No. It's a trait that the compiler automatically adds to things that are sendable according to the type system. You can't implement send yourself, so it's magical in some sense, but it's not a lifetime. A lifetime specifier would look like this. It always looks like this. I think I might be able to show you some weird lifetimes. I'm going to do this. This is very risky because I haven't prepared this. Rust probably. I'm not even sure if I have any lifetimes here, but I think I should. Yeah, cool. So. Now I just need to. So, for example, if we implement, if we want to have a struct that has a life, this means that if the stream is supposed to have lifetime A, the source needs to have at least as long lifetime. This is kind of like I don't know what I can say, but this is essentially a bit stream that is used for reading audio files. And then when you implement it, you can say that for this lifetime A, we need a source with a lifetime, and that's how lifetimes generally look. And lifetimes are really bad in the sense that they're very hard to get right. The zen moment about lifetimes is usually when you realize that you're having the same issues in C, you're just ignoring them and hoping that it doesn't fail. So the borrow checker is often very, very harsh on you, but in practice, it's very nice because it takes extra time to write the code, but compared to C, I think it almost always saves more or at least the same amount of debugging time and reduces the amount of bugs. So if anyone tells you anything bad about the borrow checker, it's probably right, but it's not as bad as you think it might be. It just reduces the risk that you write really bad code.